Alright, so sorry for the delay with the projector and all. Anyway, so we are done with our third module almost, except for the last one which I said as RSA. And the thing is, this part is very simple, as I said on last day's class itself. And we only have one algorithm in the form of RSA. We have to understand the principle of it and the way numerical can be done with respect to RSA. Alright? But prior to reaching to that point, let us discuss a little bit on the public key cryptography or the asymmetric process of doing it, because this is the first time we will introduce in the form of two keys, where one will be a public key and the other one will be a private key. Alright, so if you observe here the last two lines which I have mentioned over there, that we have the symmetric key cryptography which we have discussed so far, where we only had one key and we were doing it. That is primarily with respect to the sharing secrecy, it is okay. But with respect to personal secrecy, when you want to add on to the secrecy, then definitely we will require an asymmetric cryptography. And in the process, you will find that we will use both these two in cryptography, both the symmetric as well as asymmetric, for the understanding, so for making things much more secure, as well as to process the algorithm in a much faster way. Symmetric cryptography will always be faster compared to asymmetric, but asymmetric should always give you more secrecy compared to the symmetric cryptography. Okay, so both should be used together. Now, if you observe carefully what is happening over here with this diagram, very simple process is that we have the encryption algorithm. Suppose, I think I'll give you the second diagram, that will be better. If you observe here, what happens is, we have a transmitter which is Alice over here, which can be any name, but just a transmitter. And this is my receiver Bob. Alright. Now, first of all, observe one very important thing, that we have something in the transmitter as public key over here, whereas we have a private key is at the receiver. Now, what exactly are these private and the public key? We will discuss it one by one. But the point over here is the process involved is that, suppose Alice wants to communicate with Bob. That is, the transmitter wants to communicate with the receiver. So, after the possible authentication has taken place, that is, Bob has identified properly that it is the intended receiver, and Alice has also identified itself as the intended transmitter. If that exists in there, what will happen? Bob will share a public key. That is what is done over here. Through this public key distribution channel, okay, it will distribute a key to Alice and also to all the other intended user in that channel. Okay, for example, we have something like a Tom over here, or maybe a Jack over here, who are not the intended users, who are not the intended transmitter to Bob, but they will also get access to the public key of Bob. And if suppose those Jack or Tom, they want to communicate with Bob, they will have to use the public key as generated by Bob from the receiver. So that's why you can see at this point, we are not focusing on the other user. We are suppose using only one user, which is Alice. So Alice is using the public key as generated by Bob to encrypt the message. And that is being shown over here. Now, that public key encrypted message is now going through this insecure channel. Possibly the attackers like the Toms and Jack, if they want to listen to it, what they try to do, they will have the public key of Bob and they will try to get the data from this point. But the public key cryptography suggests is that, or asymmetric cryptography suggests that with the public key, you cannot decipher the code. You will require the private key of Bob, which is there only with Bob. Understood? So you have a generic key which is shared among the user, any user for that matter. They take care of that key and they want to encrypt the data, it is fine. But while they want to decrypt the data as sent from the intended user, in this case Alice is sending to Bob, so Tom and Jack are the unintended user. If they try to use the same public key to decipher the message, it won't work. There is a reason for it. We'll come to that trapdoor function. So the process is that in transmitter you are using a public key and you are receiving end, we are using the private key. But it is like whenever you are sending it to Bob, you have to encrypt the data with the public key of Bob, which is private. So suppose this Alice was supposed to talk with Tom, then Tom, after the authentication has been made, Tom is supposed to send a public key to Alice, which will be encrypted, and that data will be decrypted by Tom and only Tom using the private key that it has generated. At that point, Bob or Jack will not be having the access to this, thus making it more secure for communication. Got the idea? So that is basically what the process involved with respect to public key and private key cryptography. This is the first time we are using this, and it is much more secure as a process to receive the data at the end, because it is understandable that this private key will be kept as it is for the end user. Like the end user will have some secrecy with the specific key, and he can only decipher the message as per requirement. So that is basically is mentioned all throughout over here. So you can see Bob and Alice cannot use the same key for the two-way communication. There will be one will be public key, the other side it will be a private key. Alright. Now, last part of the law we to understand is that suppose Alice wants to communicate with multiple users. For example, as I said, Jack and Tom, along with Bob. So what will the intended transmitter should have? It should have multiple set of public keys, because there are three publics with whom she wants to communicate. So she will require three sets of public key. On the other hand, the intended users or the intended intruders or the receiver, whatever you call them, they will require one single private key each in order to decipher the message as intended by the user. Right? So that's how the thing works. You can see over here, Bob as the receiver will need only one private key to receive all the correspondence from anyone in the community. Why? Because suppose Bob is the receiver. Now you have Jack over here who wants to communicate with Bob. In that case also, Jack is going to encrypt the message using the public key as generated by Bob. Right? So the same thing will happen over here as well. So that is why only single public key is shared with everyone, but a single private key is unique to that particular end user who will try to use that for deciphering. So that's how the things worked up over here, and the explanation is given. Now, this whole concept is made very easy by the two equations which you look at. And the very example, the very thing that you are described over here will be implemented in RSA, which happens to be the best of the, and best I would say the easiest also, the algorithm with respect to asymmetric key encryption. So the observation you can see that the encryption side, the ciphertext will be some kind of a function of the public key and the plain text P, which is quite obvious. Now we have understood that the transmitter side, when you are ciphering the data, you will require the public key of the intended receiver, and you will have the plain text, which is the raw data. On the other hand, at the receiver, when you are receiving it, you will require a key which is private, and you will require the ciphertext, as we have done for symmetric key encryption. The same thing, we will consider the ciphertext, but we are going to apply the private key. So there will be two sides of the story. One is the transmitter side, one will be at the receiver side. Transmitter side, we will require a public key. At the receiver side, we will require a private key. Simple as that. And in all probability, they are not going to be shared at all. Okay? Public key will be shared with everyone, but private key will be intact with that particular user. So keeping that in mind, we will explain one very important concept and why this is so difficult to crack. Okay? The reverse operation, why it is so difficult to crack. To understand that, we will introduce something called as trapdoor one-way function. Now the explanation again in books and all, you will find it is very difficult, but I will give you a very small simple example and you will understand why, like what is the philosophy behind this trapdoor function, because RSA works with the principle of this trapdoor function. Now what is a trapdoor function? It is a process in which you are explaining in a way that going forward is easy, but going reverse is difficult. Like for example, if you observe over here, you have a set A domain where you have certain values of x and you have a function f of x and you are trying to find out y. So suppose y is equal to f of x. But suppose you want to find out x from the given value of y, then you will require something called as an inverse function over here. F inverse, any function for that matter. Right? Now, in cryptography, what happens is that when you are doing certain inverse, it is impossible to do the inverse operation when you are going backside. Especially when you are giving the discrete logarithm or the exponential pattern of key distribution, you will go in the opposite side. If you do the same process, if you want to repeat the same process in the reverse end, it is not possible to crack. This process is called as a trapdoor function. That is, it is only opening in the one side. Just to give you an understanding of the process, just a very good example I found in one of the website. Suppose I have given you the ingredients, okay, to make a coffee. You have given a milk, you have given a sugar, you need the amount of quantity of coffee also. The type of coffee was also mentioned, and you have a machine through which you are giving all the ingredients and you are getting the coffee. This is one-way trapdoor, right? Now the thing is, suppose I give you the coffee, the made up coffee, and I want you to find out what are the proportions of milk, what are the proportions of sugar, what are the proportions of number of times it has been mixed. That calculation you show me. Will you be able to extract the data from a coffee? No. That's basically a simple example to understand the trapdoor function. It's a one-way function. Why this is important in terms of our algorithm and RSA, in fact, that here also we are explaining in the same manner that when you are sending a data, you are using something like a public key, which is known to all. But when you are going to reverse this, when you try to decipher it, you will require that private key. Other than that, you won't be able to do that because the inverse operation will not be that simple. So to understand, that's why this trapdoor function or the utility of it is explained. Alright. So let's see about the trapdoor function a little bit here. It's very simple, but the important part is this, because this happens to be the key to RSA technique. Now, if you observe here, when n is large, where n is a combination of p and q, and it's a one-way function. Now, I guess all of you can understand what is one-way function. Given p and q are prime, and n is nothing but the output y. Okay. It is always easy to calculate n. But suppose given that you already have n and you want to find out p and q, what makes it as n? It is impossible to find. When n is suppose large, as we said, it's a very big number, and you want to find out what are the prime numbers which make that possible. It's very hard to get that right. So that is one of the way why the trapdoor function was introduced, or the term I introduced. Because this n equals to p multiplied by q happens to be the first step of RSA. If you observe here at the end, I have mentioned, this is the famous algorithm of RSA. We'll see that one by one, what exactly it is. So, the example 2 also you can see that when n is very large, the function y equal to x to the power k mod n is a trapdoor one-way function. TOWF stands for trapdoor one-way function. Meaning, given x, k and n, x, k and n, you can find out quite easily what is y. So you imagine a scenario where your y is basically your ciphertext, x is your plain text, k is your key, and mod n is the total number of sets. So this is my p and q, suppose p multiplied by q. This is my public key. This is my plain text. Suppose this is the scenario you are in. So basically by this process you can find very easily what is my ciphertext, which is given as y. But given the other way around, if I try to do the other way around, so for example, x is equal to y k to the power star mod of n, which is the inverse operation. In general, it is very difficult to find out if you don't know what is k prime. And that is what we called as the trapdoor. In our case, this trapdoor function, like the reason why we can do the inverse, because we know the private key. Understood what I mean? If this is the case, y equals to x to the power k mod of n, and supposedly y is my ciphertext, x is my plain text, k is the public key which is known to all, and this is p into multiplied by q. With this we can generate y quite easily. And suppose from this you want to find out x. So what you have to do is, you can see, but given y, k and n, it is very difficult to calculate x. So you cannot do it. How you can do it? Only if you know something like k prime. If we know the trapdoor function k prime, which happens to be the private key in our case, then only we can decipher. Other than that, it's not possible. This same principle is applicable to an algorithm which was defined in 1977 by the famous trio who got their due credits for that. Reives, Shamir and Edelman, they actually formed the first of these key and the very easy technique of RSA. That stands for the RSA as a term. And if you see the diagram, it is very much self-explanatory. So if you observe this, C equals to P to the power E mod of N. So this is with the transmitter side we are doing. And at the receiver side is the same thing, C, which is the ciphertext, to the power D, which D is the private key and mod of N is the same. And in between, suppose in the insecure channel, what is happening? You are doing something like this. See what he's trying to do in this insecure channel. Suppose this Eve person, he is the intruder. He only has the access to public key, which is being shared to all by Bob. He tries to doing the inverse operation. And he is coming up with a solution where plain text is given by square root E to that of the C, which is the ciphertext, mod of N. And this operation is very difficult to compute. Right? So the explanation over here is based on the theory that we have established, that if you don't have the private key, even if the public key has been shared with all, it is impossible to go back to find out the plain text. That is what the fundamentals of the trapdoor function is. You can go one way. Other side, you cannot come back. Only you can come back if you have certain conditions which are given as the trapdoor function and the trapdoor condition, if you say, and that condition in receiving end is the private. So to understand that, let me just show you the description of it. So RSA we are discussing. So this is basically the see. So RSA is now described over here. In the same manner, this document will be uploaded in your course space. So please look at it. So if you check here, this part is almost the same. The thing that is important to us is where we start off is here. So please make a note of the things that we are looking at. So if you observe this N equal to, step 1 is to understand N. Let us define the relationship N is equal to P into Q, which I already had told you that what is P and what is Q. So P and Q are two large prime numbers primarily, and N is the product of it. So that is given by N is equal to P into Q. Now, as you can see, the more large is the number, the P and Q, the better is the security. You will soon find why it is the one which is advantageous. Now, the second step is, please understand this one by one. Second step is to calculate based on this N, what is phi of N. Now, for that, as you can see, observe there, I have mentioned this is Euler phi function, which we had all discussed in long back. So this is nothing but explaining it or using the function of P minus 1 into Q minus 1 as the element. P and Q are known to us. So phi n is what we are going to calculate. Now, after why we need a phi n is the third step. And that is very, very crucial. I'll give you an example on that. So that is where we stand. The third step indicates that you have to choose the value of E, where E is nothing but the public key. Alright. So the E ranges between 1 to phi n. Whatever the phi n value you got out of that P minus Q and Q minus 1. So 1 to phi n, E should be lying in between somewhere. And the other condition is the GCD of phi n comma E should always be equals to 1. So these are the two conditions. You can choose any E which lies within the range and satisfies the condition. We'll take an example, we'll understand this carefully. So this E stands for the public key. Right? Now, based on that, let's encode it. So if you observe, the ciphertext C is given by plain text to the power E mod of N, which I told you in the PPT as well. So this is given by E is the public key, and it is expressed something like this: E comma N, where N is nothing but the P and Q, and E is N is the P and Q, and E is the public key which you have. So the expression is C equals to P to the power E mod N, where you can see that P value is also should lie between 0 to N. That's the condition. Alright. This is the encryption formula. Very simple technique. You will see that with example it will be very easy. you just understand, write down the steps that you are looking at. So first we are calculating n, given that p and q is provided to us. Based on that, we will find out phi n. Based on that phi n, we will find out any e which lies within the range and the condition is satisfied. Using that e, we will try to find out what is c, given the expression p to the power e mod n. Now comes the next one. So now your data is ciphertext. Now you have to find the other key, which is d, which is nothing but the private key. So the equation that holds true is very simple. We have to find out the multiplicative inverse of E, which we have done successfully long back, and you know the process of doing it. That is, E multiplied by D should be equals to 1. So the remainder should be 1. You remember the process of multiplicative inverse? That's why I mentioned over here. Just to remind you, you can go back to your previous discussion and you can find it out. But basically the process is that you multiply E with something so that the remainder becomes 1. That's what the multiplicative inverse was when we discussed about the mathematical fundamentals to this. That's why I told you at that time we are going to use it at some point in asymmetric key cryptography, right? So you have E dot D. So D is basically the inverse. E inverse, basically you have to calculate the multiplicative inverse of it. So you get the D. That's the private key. Now, that D you have to use over here. So your plain text will be C multiply C to the power D mod of N. Alright, so that's just that you have to do, and you get the final answer in terms of plain text. So it's very simple. Only the thing is, if N is long or N is large with values of P and Q, the calculation might require a little bit of steps, and there's a process of fast exponentiation that I'll let you know. But other than that, the process is very simple. You have to find out an E, and you have to find out the multiplicative inverse of that E, which will happens to be the private key, and based on that, we are going to calculate the final result. Now, let's see with an example. Very simple example. I have taken small values so that we are able to compute in fact. So if you see P equals to 3 and Q is equal to 11, which is given to us. Alright, so your product of N is nothing but 33. So step 1, we are calculating N equals to P into Q. This is how the questions also will come to you. So it's a very scoring area. Please don't lose out. So we have P into Q, which is 33. Now we have phi N, which we have to calculate using the formula P minus Q and Q minus Q. So for that, we have substituted the data and we got the value of 20. So basically what it means, from 1 to 20, you can choose any key, and 20 and GCD of 20 and E should be there, so that it should be equal to 1. So you have to choose anything between 1 to 20 which satisfies these two conditions. Right? So based on that, let us just, for the time being, let us take E equal to 7. We could have taken any other thing also. We'll see. You will soon find in this example itself that we have taken something else. We'll see that. So suppose we have taken E equals to 7, because the condition also satisfied. This is between 1 to 20, as well as the GCD 20, 7 is also equal to 1. So we find out what is D. Alright, and that is the multiplicative inverse of it. So that we are getting as 3. So the combination of the public key and the private key is looking at something like 7, 33 and 3, 33. This is the distribution of it. Now let us find out what is C. So C is given by P to the power E mod of N3. Right? Now if you observe, P had a condition that P can lie between 0 to N. So 0 to 33, we can take any data set for choosing it, if it is not provided to you. We can take anything for that matter, but here we have taken 31. Just an example. We can take anything. Right? So P is 31. So we are just distributing it 31 to the power public key, which is 7 mod of 33. So it was P to the power E mod N. So that's what we are substituting. And eventually when we calculate it, this part is, again, I can't help you, but to make you understand, this is all coming from the discrete mathematics that we have solved, Euler functions that we have discussed. So based on that, we have found out that 4 is the cryptography or the cipher text that we are getting for the plain text 31. Right? Any doubt here? Any problem? I don't think there will be a much problem. Yes, please.
So it's set that
Public key and private key will lie. This one.
last
This one. Yeah, 7 we have found out, right? 7 we have assumed here. This is my public key. This is my derived private key. So that's why we are arranging it public key, comma n, because this was there. In the previous slide, if you observe, E, comma n. So E is my 7 here and n is equal to 33. So that's what we are writing. Alright, so that's where we stand. So this is my C. Now in the same process, you decipher the data because now you have C, which is 4 whole to the power 3 because 3 is my D and mod of 33. So we are getting back 31 over here. So the process is very simple for RSA. You use this private and the public key technique and you find out what are the expression. Now this, as you say, that like as you can observe that the process is very simple, relatively simple when you are looking at when n and n or the p and q's are small. But when p and q is relatively large, it becomes really difficult to compute this process so easily. Okay, so we'll see that with an example how we can solve that as well. But just to keep you interesting on that, suppose we chose e equals to 11. Any doubt with the process that I told you now right now? Everyone is okay with it? Right. Now, as per our condition is concerned, 1 to 20, we can choose any key in between, right? So suppose we have chosen something as e equals to 11. Just for example, instead of 7, we have chosen it as 11. Because the condition is also satisfied over here. So now if you observe that for that, we are trying to find out the multiplicative inverse. And if you observe here, in both the cases, if we choose E equals to 11, your D is also coming as 11. That means your public and the private key both are coming to be same. Alright, so that is a, by default, it's a no condition. Public key and private key cannot be the same. So that's why the choosing of that E becomes very important while you are designing all this encryption technique. Alright, so you can choose anything, but it should not match the private key as well. If it does, then you have to rethink about the public key once again. You have to do a retransmission of it. And based on that, you have to redo the process once again. Right? This is one of the example. You can see it later in the course page, which you will find. Right? So in that way, we can find out that this RSA technique is very convenient in doing it. For example, this is another question in which we are considering P and Q as 17 and 11. Okay? In this particular example, 17 and 11. So, and the message is also given as 88. Unlike to the previous example where we have chosen 31 as just a value which lies between the element. So here we are choosing my P and Q is provided 17 and 11. And the question is to find out the ciphertext and decrypt back the 88 data. So the same thing is processed over here. Same thing, n multiplied by q phi n lies between this. So you have a key range between 1 to 160. In this case also we have chosen something very small which is equal to 7 and we got the answer over here as the final answer which goes on. You can check it later and the final answer is 88 once again. Okay, I'm not going through the question again because it is immaterial. You can just look into the course file and you will find that how it has been done. It's very simple actually. You can see the process. It's nothing here except that here 88 to the power 7, you can break it into different elements like this. You remember this process, right? We have done this in Cat 1 and the same thing is applicable. So you get the ciphertext as 11 and that 11 is used for the second part of it and we get the plain text back. Now the point is the last part where we want to discuss is something where when the key is pretty high, long. For example, I'll just give you an example over here. Let's see. This all we have done almost. Suppose this one. Now, when you look at this example, okay, you observe that P and Q is relatively large, very large in fact. And in that way, the calculated value of n is also coming pretty high. Alright, so your n is like this. So phi n is calculating like this. Okay, so phi n then calculates the phi n of this also. So 158400. Alright, so in a way, so then he chooses something like this, D comes in like this. It is not calculated. What the idea is behind to show you this, that when you're doing this kind of a process, it becomes really difficult. When the n value is long, you have to have your E which is even sufficiently high. Okay, so that is where the calculation, normal calculation will sometimes be of real difficult job. And that is where something we will understand in very simple language, and that is called as fast exponentiation. So let's see whether we can understand that, and that's where we end our discussion. So let's see whether we can understand this. All right. So this is called as fast exponentiation. Okay. It is nothing to exponentiation. Fast exponentiation process. This is nothing to do with specific to RSA, but it is a technique in discrete maths which we have not discussed up till now, and we don't need that. But we hadn't needed up till this point, but this is where it needs, where the power is to be pretty high. For example, this is not exactly the example, but still I'll just give you that example. For example, 240 to the power 262 mod of 14. This is not a prime number and nothing. You can see that 14 is not a prime number. But suppose you have a scenario like this. Alright. Then we have to have a process of doing it. That is what we call as fast exponentiation. So understand the process, and that's what you are going to apply for scenarios as given in the PPT, where the to the power part is very high. And also the n, suppose this is my n in our RSA, suppose that is also pretty high. For example, I give you a proper example, maybe 2 to the power 23, suppose this is the example, 2 to the power 223 mod of 353. Suppose this you have to calculate. Your process of RSA in the ciphertext calculation, this is what we are doing. But suppose you want to calculate it normally, you will find real difficulty in solving it. So how we are going to do it? So for that, this fast exponentiation comes in. So what we have to do is, the process is, first we have to make the binary, the exponent part, the 262 over here, this part, this you have to convert into binary exponent. So convert it into binary equivalent. Just note down this. So how we are doing it? 262, you check later, you will get it value as 1 0 0 0 0 5 0 1 1 0. So this is in binary, will convert. Binary, you know that 262 divided by 2 and all those stuffs, you will do it and you will get this final answer. So first step is, you have to take the exponent. This is my exponent part. Okay, this is my base. Alright. So now the exponent has been represented like this. Now you form a table. How you form the table? You just make sure you write all the elements one by one. 1 0 0 0 0 0 1 1 0. So I'm just writing down the binary data, binary bits for that matter, in a table format. Alright. Now the first step is, the first entry on this table will be the base. That means here you write 240. I'm explaining the fast exponential process, in which we have to first convert the exponent into binary equivalent, then we have to design a table in which we are writing like this. Now this is usually called as a square and multiply method. Why? Because based on what the binary equivalent data, you have to form two steps. We'll see what are the steps. The first step is, you check what binary data is over here, which is 0. The bit is 0. So what we have to do is, we'll just need to do this. 240 square, suppose this is my step 1, mod of 14. Just do this. Alright. So first element will be the base square, mod of 14. Mod anything we can do. So this answer is giving us 4. It will give us 4 answer. Very easy. You can calculate and let's check. This 4 that you are getting, substitute this 4 over here. Alright. 240 I have taken, and I have taken the first round. As 0 is there, we will only require the square. As this is 0, we are only going to do a square to the previous data and we get the value 4. This comes in as the input over here. Now, next data is again 0. So, we will do 4 square mod of 14 and we get a value. That 2 is substituted here. Now, we take 2, that is 2 square, this is the third step. So, 2 square, this is my 0 again. So, 2 square mod of 14. We get the value 4. Fourth step, 4 square mod 14 as there is again 0 over here. So, again the outcome will be 2. Correct? And naturally next one is also 0. So, for 2 we have already calculated. So, it will be 4, something like this. Now, you check this. Now, you check this. When we have 1 over here, this is very little different to that of the previous one. We have to do 2 steps. One is to take the square of it. So, we will take. So, we are somewhere here at this one. So, 1, this is 4, 5, 6, maybe 6 step. So, what we are going to do, 4 square mod of 14, which is equal to 2. But as the binary bit is 1, we have to do another step where we have to multiply 2 with the base. That's the only difference. And the resultant output will be mod of 14, and that's the answer for 4, and that you have to replace here. What again? All the zeros, we don't have anything to do, only the squaring is enough. But when there is a 1 for the binary data, binary bit, we have to do a square option. Whatever the output you are getting, multiply that with the base. Base for this, for example, is 240. So 2 into 240 mod of 14. Whatever be the answer 4, that you replace it. Same will go here. Here also there is a 1. So it will be 4 square mod 14 equals to 2. Then again 2 you will get 2 multiplied by the base again. So this will again be 4. That you do it with next one. So 4 square. 0 it is. So it will be only 4 square. Now 4 square we have already found out. That is 2. So your final answer for this. So this will also be 4. And this is 2. So the outcome of this fast exponential process is only 2. So for all this thing, what we are trying to do is to find out what is this equivalent to. So this is nothing but using this technique of fast exponentiation, we can find out using this tabular approach without doing any much problem. For any such element, you can find it out in this way. Alright, so first you have to convert the exponent into binary equivalent, make a table of this nature. Remember the simple rule that whenever we have zeros, we only have to do a squaring of the element. And if there is a 1, we have to do square and multiplication of the base. That's the only change. So I want all of you to please look into it for this element 2 to the power 23, as I said. Just send me the answer for this. Mod of 353. 2 to the power 223 mod of 353. Do it using the fast exponential process and tell me the answer what you are obtaining after this. Alright. So please do that. And so when we come back next day, so this ends our discussion on module 3. On Friday's class, when we come back, again we are going to discuss the one very simple rule with respect to key exchange, okay, which is the starting of the 4th module, and that also we'll explain with an example so that you can solve it easily. So I'll let you know the final syllabus only by Friday. So don't miss out the class. Correct.